Okay, I think we've got enough people back to get started again now. So I will get started. Before we get started with the material for this afternoon, I just wanted to quickly check if there are any questions or what questions people might have about the stuff from this morning. Yes, Stephen. Was that just a mistaken hand, or did you want to ask a question? Okay, that's fine. Does anybody have anything from the stuff we covered this morning that they wanted to ask before we get started this afternoon? Nope, not hearing anything. Okay, we'll just get started then. So just a reminder of where we were up to. We just started to talk about how we might build our own container image. That's so starting from an existing container image, possibly usually from the Docker, but maybe potentially from elsewhere, and then adding packages to it or adding software to it that isn't in the existing container image. And if you remember, we managed to get an interactive shell within the Alpine, an Alpine container, starts from the Alpine container image. We managed to install Python 3 and then install Cython on top of that. And the question is then, how could you do that rather than doing it interactively, because that's lost when you exit the container. There are ways to snapshot it, but we're not covering them in the session, and it's generally not the best way to do things in terms of reproducibility aspect anyway. How can you do that using the Dockerfile, which is the definition of the recipe for creating a container image? And we have this template Dockerfile, which has these sections with from, where we're going to define what the existing image of starting from is, to run the commands that we want to run inside the container when we build it, and then defining the command we want to run by default if somebody runs if somebody starts a container from the container image, but doesn't specify the command they want to run. Okay, and the exercise here was to take a guess and see what we could put in there. What I'm going to do is I'm going to edit the Dockerfile. You can use whatever editor you prefer. I use VI just because that's what I'm used to, but you could use text edit or whatever the one on the Mac is, or whatever you prefer, Emacs or something like that, to edit it. So I'm going to work through this exercise together. So we're going to start from an existing image. Now, we start the interactive image we started with was the Alpine one. So we're going to start from there. So let me change that to Alpine. So we're going to start from the Alpine image from Docker Hub. And then we want to run the commands we used to install stuff when we did the interactive access. So the first command we ran was the command that installed Python 3 and various dependencies, which is this apk add command. So we're going to add that in there. And the second command we ran was the one to install Cython. So we're going to add that command here. And then the command we want to run by default. So since we're installing Python here, it makes sense that the command we're going to run by default maybe is Python 3. If the user doesn't specify what command they want us to run, then we'll run the Python 3 command. Oops, sorry, that was just me hitting the wrong bit of the keyboard. Okay, so now we have a definition file, the Dockerfile, that specifies the recipe to create this Docker, this container image from an existing container image. And it replicates what we did interactively, but the idea is at the end, it produces a new container image that is based on Alpine, but has these extra bits added in and is saved in that way, okay? So if I look at the solution, hopefully it matches what I actually, if I look for the solution for this one, it hopefully matches what I added there. Oh, of course, okay, so I remember I said that we were going to use the command form the sort of new command form, the exec form, And let's add Python minus version as it says in the exercise solution. So we're going to get the version from Python. If we don't specify a command, it's just going to return the version of Python 3 installed in the container image. Okay. So now we've got our Dockerfile. I'm going to save that. Now we've got our Dockerfile. We need to actually create our container image, and we need two pieces of information for that. One is the location of the Dockerfile, and the other one is the name of the new container image. And if you remember back to when we were talking about the Docker Hub, we talked about a naming scheme for container images, particularly if you're going to use the Docker Hub. So you can give your image whatever name you like, but if you use a format that's like this, which is your Docker Hub username, then a slash, and then the container image name, then that sets it up to be ready to be pushed up to the Docker Hub if you want to share your image that way. Okay, so they're putting the plan together. We get the Docker image, and this time we're building, because we're building an image. The -t option is short for tag and gives it the container image name you want. And then finally, the name, your username, the name of the image, and then this dot at the end, because we're running the build command in the same directory where we have the Dockerfile. So that says the Dockerfile's in this directory, okay, because dot refers to the current working directory. Andrew says, can I include in the Dockerfile a command to install a library inside Python? Yes, you can, because you see that one of the commands we have is pip install. Okay, so that that installs the standard ones via pip. Now, in a minute, when we look at complex container images, we'll show maybe how you can install and add, say, your own Python module source files you could add into the container image as well. If you want to, say, had custom Python modules which you built, and you wanted to push those source files into the container image itself. We'll show you how to do that in the next bit. Okay, so if my username was Alice, which it isn't, but I'll show you mine now. And I wanted to call my container image Alpine Python, you could do something like this. So I'm going to do this, but I'm going to use my actual Docker Hub username to build. So I'm going to go, so in this directory, all we have at the moment is the Dockerfile. So Docker image build, -t for the tab to give it the name. My Docker Hub username is Eterna EPCC, and then I'm going to call it Alpine Python, and then I want to tell it that the Dockerfile is in this directory. Okay, and then I'm going to let Docker go away and create a new container image based on the recipe in the Dockerfile I've given it. So I'm going to press return there, and off it goes. So it does a few different things. Some of the things you can see is that it's used. The first step was to get the from Alpine, which is what it's done here. It was already locally, so it didn't need to go and pull it. The second step was to run this APK add update pipe. That was to install the Python stuff. You may have seen it quickly go through all that installation as the lines where it's whizzing past there. The third step was to run the pip install siphon, and then the final. You don't get no notes about the command one, but it tells you it's exporting it to an image. Writing image, blah, 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 and naming it, giving it this name. And you can see it's implicitly stated that it's going to push it to the Docker Hub. Okay, now, so if I do Docker image ls, you can see here is my new image that I've built. And we had the question last time about earlier this morning about what this created means. And you can see this one was just created 40 seconds ago. It was when the image was created. Not when the file was copied to or when the image was copied to the system. And that's just specifying that where it needs to find the Docker file. Okay, so this review in the exercise, what command can you run to check your image was created successfully? So that was what we've just done, Docker image ls. We didn't specify a tag for our container image name. What tag did Docker was going to use? Well, as we said earlier, if you don't specify a tag, it uses this magic tag latest. To do that, if you'd want to specify a specific tag, we would have had to put a colon and then the tag here, whatever you wanted. But I'm not going to do that right now. And what command will run the container based on the image you created. What happens if you run such a container? Okay, so we could try running our container. If you remember, the command to run the container is docker container run, and then we're going to give it the name of the image we want to run, and it prints out the version of Python in the container. It's worth noting that that's different from Python on my system. I could put Python 3 in probably, which is 3.8.10. That's my host system Python. The Python in the container is 3.9.7 because that was what was installed when we did the installation of the container. Okay, so this seems so simple. I mean, and one exercise you could try is, can you make the container do something different, like print hello world? Well, the way we could do that, of course, is to give it a command to run instead of the default action. Okay, so hopefully you've all managed to, hopefully you've all followed along. You managed to at least start to think about creating a container. I encourage you, we're going to reuse this Alpine Python container in the rest of the lesson, so please go ahead, create the Dockerfile and build the image locally on your system. I'll just give people a chance to do that, and I'll talk away. Yeah, so just that's when adding the hello world, the command is not triggered. No, because the command option is the default thing to do if you're not told what to do. Okay, so in this case, we were telling the container that we wanted it to run this command. Okay, but when we ran it before, we didn't specify what command it should run, so it fell back on the default action, and this CMD in the Dockerfile defines what the default action is if you're not given a command. Okay. So if you don't have a Docker Hub username, yes, you can just use Alpine Python without specifying a username. That's perfectly valid to build it. It means the reason you do this is for pushing up the image to the Docker Hub. If you see, you want to be able to share the image. It's up to you whether you want to go ahead and get a Docker Hub username and push it up to the Docker Hub. And I'll show you that working in a minute anyway. Okay, but you absolutely do not need to have a Docker Hub username to use Docker on your system. So while people are building the image, and I'll put a poll up to make sure at the end to make sure that everybody's managed to build the image build this image locally, because we're going to carry on and build on top of that. Just to say, it doesn't feel like you've done very much, right? I mean, we just did we created a very simple Docker file, just 4 lines. We issued a command, docker image build, and it just did some stuff very quickly, and then we ran it. But what you've actually done is put a lightweight Linux operating system designed by you into a container that you can then reuse on any platform. So you could take this container image you've built now and take it to a different system, be it Windows, be it Linux, be it somewhere on the cloud, and run exactly the same image and run a container based on exactly the same image and get exactly the same results as you would on your host system here. So you've created a very portable, bundled up set of software and components and environment setup that you can take with you wherever you go. So as I said, in terms of installing stuff, you use a Python command rather than using pip as a shell command. Is it possible? Yeah, so what you're seeing here in this Dockerfile is any command that you can run, virtually any command you can run on a command line interactively within the, if you're in the container on the command line, if you could run that command there, you can build it into the Dockerfile and run it there as well. Of course, if you're using the Python command to build and install software, you would first have to install Python in this case. Okay, so it would have to come after this step. how come the preferred syntax for run is plain text, but command is the list thing? Okay, so do you mind if I defer that one? Partially because I'd have to double check that I was giving the right explanation before I did that one. Yeah, and I don't want to give you incorrect information about why it's like that, Jamie. So I'll look that up and get back to you exactly why that is. I don't know, I can't remember off the top of my head. Andrew says, so I need to invoke Python 3, then a Python command. Right, yes, so that would just run in the same way as you were running it locally. That would run the command. And we'll see a bit more of that, hopefully, in a bit. So some notes on top of what we've done here. So even though it's going to be powerful, some notes to help you when you're building your own container images. So don't install everything from scratch. Start a bit clever. There is a lot. If you're using Python as your main tool, start with a Python container image. Same for things like R. Start from an R image. We started by using Alpine Linux as an example of this lesson, but it's not really a good place to start for initial development because it's a less common distribution of Linux. Using something like Ubuntu or Debian and CentOS, even though CentOS, there's been some changes to CentOS recently, are better options for scientific software installations. We've used this one here because it's very small, so it means it's quick to download and people don't wait around a long time to see things happen. If the core program you're using, the bit of software you're installing, recommends a particular distribution of Linux, then consider using that as the starting point. How much software do you really need to install? Get away with the minimum possibly you can, because a bigger container image is more difficult to handle, more difficult to distribute, and more difficult for people to download. Know your Linux. As we mentioned, containers are all Linux based, and you'll spend a lot of time using the commands that these sorts of distro commands to install software in them. In Alpine Linux, it's APK. For Ubuntu, it's apt or apt-get. For Debian, it's deb, and for CentOS, it's yum. And for SUSE, it's zipper, I think. Okay, so understand those commands, what they could do, and what's available to be able to be installed. Use what you know. You probably use commands like pip or install packages before on your own computer. These also work to install things in container images. I think that's what we're talking about here between Andrew. With Andrew, you should be able to do exactly the same things you've done. Brian.
Yeah, I just wanted to ask whether it would make any sense to install Conda within your Docker container and then install the rest of your packages using Conda to get an additional layer of ensuring that all of the versions of the different packages that you're installing are compatible.
Yeah, I mean, that's certainly possible. I mean, Conda adds more size, right? So there's a trade-off between using what you know and building on Conda and adding more size into the container. And, I think there's a more complex discussion here a bit, right? Because Conda itself is trying to solve sort of this problem as well.
Mm-hmm.
So you can specify Conda environments and things like that. So if you're purely Python based, there is also the option of saying, well, I'm not going to use containers at all. I'm just going to distribute Conda environments and things like that as an option. But using a Conda environment or using Conda install within a container is certainly a valid approach. I don't think there's any.
Yeah.
The only reason I could think it would be a problem would be because of the size of the image you might get to.
Yeah, and Conda is great on its own. It doesn't necessarily cover all the bases that the Docker or Singularity container covers.
Yeah, no, I mean, exactly. So if the easiest way to get the stuff into the image is to use Conda to do it, then that's just fine. You may just have to keep an eye on the size, and it might just make it a bit bigger than it would be otherwise.
Cool, thank you.
Yeah, and README. Most software tools that you install comes with README. Look at the README instructions for Linux for the pieces of software you're interested in. Do they specify anything in terms of in sort of options or things that you might need to get things installed in the container image? So a general good strategy is to make a list of what you want to install. Look for pre-existing container images. Read through the instructions. Try installing everything interactively in your base container and take notes as you do so, or capture what you're doing in some way. And then from your interactive installation, create a Dockerfile and try to build the container image from that. Yeah, so Joris is asking, can we create a Dockerfile based on interactive installation, like save option? Remember what you did. So you can. I said there were commands for that. We can. I can look them up and I'll put them in the shared document how you can snapshot it. But and then how do you get the Dockerfile out of that? I'd have to double check that. I don't know off the top of my head. I have to say. Lucy.
Hello, I'm just wondering, would it be possible to create a Docker image with Jupyter notebooks installed so that somebody could run a notebook and it pop up in their browser and they could run through that notebook?
Yes, and there are Jupyter. I'm 99% certain that there are official Jupyter notebooks out there on Docker Hub. I'm sure I've used them, in fact.
Because everything so far has been very much based on the terminal. So I was just wondering if there's anything limiting it opening up, you know.
No. You have to do, there you go. So there are official Jupyter notebooks. So this is the Jupyter TensorFlow, but Jupyter have various ones of them. And it tells you how to pull them. And somewhere, there you go. There's information on how to use and how to run containers, and there's some extra options. You have to bind ports and things like that. But there's actually Jupyter is have a lot of information that's already common usage of Docker. I'll put that link in there in the chat. And I'll put it in the shared notebook as well. Cool. There you go. So absolutely, you can do graphical things and have graphical interaction with notebooks, particularly using the browser, things that appear in the browser. So the final step in this section is to push the image up to the Docker Hub. For people who don't have a Docker Hub username, this won't work, or you can skip it. Or you can do that too, yeah, from the command line. You can search rather than searching on the website if you want. You could use the Docker search command. So I'm going to Docker image, push, and then give the name of the image I just created. And off it goes. And what it does is it uploads all the bits and pieces from my container image up into the Docker Hub. And it will tell me where it comes from. Now, Docker's quite clever. It knows that part of my image came from the already existing Alpine image on the Docker Hub. So it says, actually, I don't need to push that because that's there already. So I'll just reference the bit that's on Docker Hub already, and then when people and that I don't need to use your bandwidth to push this bit of the image up, so things can upload much more quickly. And that should be just about it done. It's not far off done anyway. And if we now go to hub docker.com, oops, sorry, I didn't want to do it that way. I can sign in because it's forgotten who I am. Yeah, I told you my password. Okay, and here's I've got a few other images that I've been messing about with, but this is the one I've just pushed up. Now it says updated a few seconds ago. Of course, nobody in their right mind would pull it or use it because it has no documentation or any of the things I mentioned associated with it. So it's just random image that some random person has pushed up to the Docker. So Lorenzo's asking about creating an image from scratch. I have to say I've never ever done that, because the closest I get to creating an image from scratch is you have to start somewhere, even if it's just with a Linux distribution. You have to have some sort of operating system. So almost always you'll start from something like Ubuntu or CentOS or something like that. or if you're doing something very lightweight, and you might use something embedded like the BusyBox stuff, or even Alpine Linux. But you always have to start from somewhere, essentially. Now, I could go and look up, and I'm guessing that there may be ways to create an image totally from scratch. I've never explored it myself, I have to say, but because you're going to have to build on something to a first approximation. So you could create an image, but then you'd have to install an OS anyway, right? So if you just started from the bare kernel, you'd have to use some installation media for Ubuntu or whatever you're starting from anyway. So you may as well use their official container images. So I don't think in real practice that's a approach that's useful, because you've got to have an OS. So I'm not sure what use case you're thinking of, maybe then is what that question comes down to. Yeah, you can see have more minimal things. I mean, people do things like you can do a two-stage build process where you install things and then strip out the bits you don't need after you've done the installations, like the dev headers and things like that are no longer needed to minimize the image size. But unless you're running in like something that has really low amounts of resources and memory, like typically an embedded system, like a fridge or a light bulb or something like that, then it doesn't make a huge amount of sense. Yes, you might have something like from Ubuntu, and then a whole list of run commands that reproduce your current work settings. Generally, you try to combine them into the smallest number. Okay. So we now push this up to Docker Hub, and somebody could pull down it. Anybody can now pull that image if they want and use it. Though, as I say, nobody would really do that. And you don't have, as somebody said before, you don't have to name your container images using this. On your own system, you can call container images whatever you want to refer to the names you choose. It's only when you're sharing the container image that needs the correct formatting. And if you build an image with a random name and then you want to reform, you want to actually decide you do want to push it up, you can rename it with the Docker image tag command. So you could rename the image that you've given a random name up into something that has a or you can create a tag that references that image that has the correct format that you can be able to push up to Docker Hub if you wanted to. Okay, so that was quite a short section, but we've actually made a lot of progress there from now from just being able to use other people's images. We can create our own images based on starting from what people have done before. Okay, so the next step we're going to look at is creating more complex container images, right? So one of the things that a few people have alluded to already is, what happens if I want to get data from the host system into the container image, right? Because it's all very well being able to run commands, but you need to be able to run commands usually on some sort of data, and that data is not likely to be in the container image itself. Okay, so you need a way to be able to access data from the host system in the container image in some way. And that's what we're going to look at here. So you might want to use files from outside the container and distribute them with the container image. That's fine. You might want to actually run on data that exists on the host files on the host system, but use the tools that are inside the container image. So we're going to have a look at how we do that. There's some more bits and pieces at the end that I'm not going to cover in any detail, that you're welcome to look at yourself or ask questions about later on or as the course goes on, that cover sort of slightly more esoteric cases. But most day-to-day situations, the stuff we're going to do in the first one or two sections of this lesson, plus the stuff you've learned already, will cover what you need to do. Okay, so now we're going to go into a different folder in here. So rather than the basic one, we're going to go into the sum subdirectory. So I went to upper directory and then into sum. And in here, we've got both a Dockerfile and a Python script called sum.py. So we've got a we've just built a container that's got Python in it, and we've got this Python script, which I'm going to cut. It's very silly Python script. All it does is sum up all the arguments and supply and print out the total. Okay, it's a very simple Python script. So now we can try and use our, I'm going to skip back, where was our Docker container run. So what we might want to do is actually just try and run. We know Python 3 is in there because we can do this. Sorry, is in the image and in the container we create from the image. Perfect. So let's try and run our script in the way we would normally do it, but with all the container stuff at the start. Okay, and the problem is, of course, that sum.py script is on the host system, not in the running container. So how can we fix that? In order to use Python inside the container on our script that's outside the container on the host computer, we need to create some sort of link between our host system and inside the container, so the container can see the data that's on the host computer. This link's called a mount, and it's what happens automatically actually on any system. When you put a USB drive into the USB port on your computer, it mounts the file system or mounts the data on the USB drive onto your system, and you see the contents appear as if they were on the computer itself. So we can do the same with Docker containers, and we create a mount inside the Docker container. That means it can see data that's on the host system. We're going to use an additional option to Docker container run, and we're also going to use this shell variable $pwd. PW stands for print working directory. So if I echo this on my host system, oops, if I could actually type and get the braces the right way around, it prints the full path of the current directory I'm in here. Okay, so that's telling, that's a piece of information that the container needs to be able to mount, to know what it's mounting within the container. So the option is going to look like this. So we're going to have -mount, specifies the mount. The type is going to be bind. The source directory is going to be this local directory I'm working in, because that's where the sum.py script is, the bit of data I want. And the target, the location it's going to be mounted within the container itself, is going to be at /temp. Okay, I've chosen that because that's not one of the standard sorts of Linux directory names and things like that. There's usually a /tmp, but there's not usually a /temp. I could have called it /hostfs or something else, but I'm called it temp here. So what this is meaning is make my current working directory on the host computer, the source, visible within the container that's about to be started, and inside this container, name the directory temp, which is the target. We set the mount. You'll notice that we set the mount type as bind. There are other types of mount that can be used in Docker, volume and tempfs, the two of them. We don't cover these other type of mounts or the difference between these mount types in this course. It's a bit more of an advanced topic. You can find more information on different mount types in the documentation. So if you want to know the difference between them, do that. Okay, so now we've got a full command. We've got this extra command with these extra options in it. So let me go back to the command I was running. Oops. Is that, there we go. Okay, so I've got Docker container run, and I'm going to add, in these options, I'm going to add this extra mount option here. Oh, sorry, I have just realized I forgot to put the poll up to check that everybody had managed to build the container. I'll do that now, once I've done this, once I've shown this. So this one says we get the same error, but I'll come back to that now. Just let me put up a quick poll so I can double check that everybody's managed to build the container, build the Alpine Python container successfully. I can't spell, of course. Sorry, I should have done that before I started this section. I totally forgot. So can I ask them help us if people have answered no? Can you go and double check with them what the problem is and help them out if needed. It looks like most people have managed to get that working on their system, I think. Okay, so I'm seeing a lot of yeses. There is one no, so if somebody can go and help out, please, that would be much appreciated. One of the helpers can go and help out people who've not managed that. The person who's not managed that, that would be great. Thanks. I'll stop that poll now, but it seems like most people. Sorry. So back to here. So I added the mount option, which I claimed would. Just give me a second. Someone just ask you a question. So I've added the mount option, which I said would magically make this data available in the container, but it still doesn't work. And the reason for that is because you have to imagine you're inside the running container itself. Now, okay, inside the container, of course, the location of the sum.py script is at /10 because that's where we've mounted our current direct working directory within the container. So you have to imagine yourself in the container and where that might be. So the actual modification I need is to specify where the sum.py script is kept in the container, which is in /tamp, because that's where we've mounted our working directory in the container. So that's the only bit that's missing. My finger's gone off the side of the screen. So I need to add /tamp sum.py to specify the full locate path to the sum.py script in the container itself. So let's try that instead. Okay, so now it says sum equals 0. So actually it's giving us some output. Okay, so it's because we didn't supply any arguments, the sum is 0. If we'd said something that wasn't really an integer, that didn't look like an integer, we'd get an error message. But because there's just nothing, we just get sum is 0. And you should note that actually this is even more powerful because if our container creates any data in this /temp directory while the container is running, these files appear on our host file system and persist after the container's exited. Okay, so once the container stopped and exited, any data we've created on something that's mounted in the container from the host file system stays there as well. Okay, there are some other commonly used Docker run flags that people can use. One is to specify where you want to run. You can specify your working directory. So that says, when I'm in the container, act as if you're in that directory. Yeah, Lucy, so that's that final step I just covered there. So because sum.py isn't in the same directory in the container as it is in the host, if you see what I mean, it's not the same path anyway. Because we mounted our working directory at /temp, the sum.py script is also at /temp, so you need to give the full path to it to tell the Docker container where to find it inside itself. It's a little bit tricky because you need to picture yourself inside the Docker container and what the container is actually seeing in terms of paths and file systems. So it is a little bit fiddly trying to imagine yourself in the container's shoes. Two commonly used flags. You can specify the working directory, so that's when you're in the container, it shifts automatically to the directory you specify. So I guess one option there would be, instead of giving the full path to sum.py, oops, if I could type, is to instead change my working directory to /tmp. Let's see that, /temp. This may work. I've not tried this before. Yeah, that works as well, because what that means is that when I go into this option saying when you go into the container, move to this directory before you start doing anything. Okay, so now you're running as if it's in the current directory. And also, somebody asked earlier about if you're always root, you can specify that you want to be a different user and not root. So you can behave as if you're actually just the current user in the container if you want, and that gives you more protection, I guess, in terms of deleting files accidentally on your host system if you're mounting file systems in there. Yeah, so Luke asked, does the working directory need to exist in the image, or will it be created? It needs to exist in the image. It won't automatically create the working directory for you. I'm saying that very confidently while thinking, ooh, I've never actually tried that, but I'm almost certain that it won't create it. If the working directory just doesn't exist, it will just complain. In fact, we can test that, can't we? Let's change it to something that doesn't exist. Okay, so okay, it says that file doesn't exist. It hasn't complained about changing to that directory. Not sure. I'd have to do more investigations there. Okay, so let's try. We said that the script should add up some numbers, so let's try using Docker container run command and put some numbers after the script name. So that should be easy to try. So here we are back with our one where we're specifying the full path to sum.py, and I'm going to give it 5 and 6. Okay, that seems quite good. It's adding up the numbers for me, which is what the script was claimed it would do. Okay, so the script's working as expected. So we're using a script that is installed on our host computer within a container with the Python that's installed within the container image, within the container that started from our container image. So you can see actually one thing that has happened is that our Docker run command's got a lot longer, a lot more complex. So we should go through and check that you understand what each of these sections are doing. So you can ask everybody to have a look at the Docker run command with all of these options in, and if anything's not clear to you, put your hand up or ask in the chat, or just shout out and ask in person. I want to check that everybody's comfortable with what all the options are doing here now in the command before we move on. I'll just give people a couple of minutes to have a think about that and have a think if they have any questions or if anything doesn't make sense to them. Okay, I'm not hearing anything, so I'll go through them. I'll go through it just quickly. Docker, obviously the command to run Docker. Container means use the container subset of commands. Run, because we want to actually run a container based on the specified container image. The mount option specifies that we want to make some data from the host file system available within the container. The types bind, we specify the location on the host file system, on the host computer and the location we want it mounted at in the container itself. We specify the name of the container image we want to base our container on, and then finally the command we want to run in the container once it's running. In this case, Python3 run this script, and then some extra parameters there, which are the numbers we want to sum together, the data we want to operate on using this script. Okay, and the other thing you could do, of course, is mount your, if I mount my container interactively. I've gone back too far. I'm going to go back here. I'm going to take away all the temp sum.py stuff and the Python3 because I just want a shell. And remember, if I want an interactive container, I have to add the -it options. You can see ls, and if we go to /temp, which is the place we mounted from the host file system, you can see both the Dockerfile, which exists, which does exist here, which we haven't looked at yet, and the sum.py script. And it's the same script. We had it there. If we added a random file here and put some text in it, and then exit the container, back here you can see that's created the file t.dat on the host file system because we were operating in the place where the host file system was mounted within the container. I'm just going to get rid of that file because you don't need it anymore. So mounting a directory is really useful when you want the software inside your container to run on data that exists out with the container. But in other situations, you might want to add or archive some authoritative version of your data or some components of the data within the container image permanently. So maybe it's some configuration parameters that go along with the software that you're wanting to run, that you're wanting to distribute, or you want to capture the analysis script that you've written in, say, Python or R, and distribute it along with the container image because it's part of the provenance of the analysis that you've been doing, or whatever, or the research you've been doing. So you can do this. We're still in the sum folder here. See, sorry, there was a question there. Let me can you use the same command to copy output to the host system? So you mean what command are you referring to here? Sorry, I'm not quite sure I understand.
So the type, the mount command, the mount option, for example, specifying source as a /temp and target as a print working directory. Does it work?
No, the target is always in the container and the source is always on the host.
Okay.
Okay, but as you've just seen, I was in the container and I created a file and then it was visible on the host, so it doesn't really matter.
But for example, if I want to get out on my host system to be copied to my host system.
So that's what I did. I just showed, sorry, that wasn't clear. So I created a file in the container and then it was available on the host file system.
Oh, okay. I didn't notice that.
Okay, so because once you mounted the directory, when you add files within that directory, they appear on the host file system too. You're writing them into the host file system as well as making them available in the container.
Oh, okay. I missed it. Yeah, I understand now. Yeah.
Yeah. You can also add multiple mount commands. So if you wanted to mount different directories in different places, you could have multiple mount commands and make different directories on your host file system available at different places in your container.
Yeah, thanks. Makes sense.
Okay, Brian.
Yeah. So the only way I'm familiar with binding mounts is when you're actually creating the Docker container. But I was wondering if you already have a Docker container created, and let's say you forgot to bind a mount, or you want to add a new one. Is there a way to do that once it's already been created?
I'm not sure is the short answer to that.
Okay.
I'd have to go and look. I'd have to go look. I usually because starting and stopping and exiting containers is quite low overhead, the usual approach would be, oh, I forgot to create that mount, I'll just exit and restart the container.
Right.
But yeah, I guess there was the case where you've been interactively using the container and done a lot of work and then realized you've forgotten to mount the right place. Where that's the sort of edge case you're talking about here. I've not tried that. I don't exactly know how to do it. Again, it's another thing I can go and look up and see if it's possible.
Cool, thank you.
I don't know if there's some sort of Docker modifier or Docker add mount command, but I've got a note of these questions and I'll go and check them out.
Great, thank you.
No problem. Okay, so this time we're going to look at how to copy data in when we build the image, not at runtime, which is what we've been looking at so far. Okay, so now we're going to add a new line to the Docker file we've been using so far to create a copy of sum.py. Let me double check what's in this Docker file. Okay, so it's still the blank one from before. So what I'm going to do is copy the one we've been using from before, which was in the basic, wasn't it? To here. So now this is the Docker file that we use to create our Alpine Python image. And we're going to add a line to it which asks it to copy a file called sum.py into /home within the container. Okay, so if I edit that Docker file, copy sum.py into home. So what this line is telling it to do is do all the usual stuff we've done before and then copy the file from the host into home on the container when you're building the container. And then what we're going to do is we're going to build this image in the same way as we did before. I'm going to tag it slightly different though and call it alpine-sum instead of alpine Python. So I'm going to do Docker build, Docker image build -t. What was it? Alpine sum? Yep. Alpine-sum and dot again to tell it where the Docker file is. So off it goes. It should do exactly the same sorts of things before. You see, it's super quick. That is because it remembers what it did when it built this image before, and it knows that it already did those two steps of these two steps, so it's cached them. So it knows that it doesn't need to repeat them. It can just use the cached versions that it has from when we built last time. And then it does this extra step, which is copy sum.py into home. Okay. And now when we if we go to, where was I before? Okay, so if I get rid of the mount this time, I'm going to run an interactive container in the new one I built. I'm going to get rid of the mount option for the moment, just to make sure we're not confused. I'm going to leave IT because we're going to make it interactive, and it's going to be Alpine sum this time, not Alpine Py, because that's the new image I built. We're in the container now because our prompt's changed. And if I go to home, so you'll see sum.py is there. Okay, now. And this was incorporated at build time. So I can add a file here. Oops. If I want to. So now there's sum.py and t.dat. But if I exit the container, which t.dat hasn't appeared because there's no mount. Now, this home/home only exists in the container. You know, it's not mounted from the host file system. If I run it again and go to home, sum.py is still there, but t.dat isn't because it's not maintained. I've started a new instance of the container from the container image. So sum.py is there because that was part of the definition of the container image, but the t.dat isn't because that was something I created in the last running instance of the container, and this is a different running instance. Okay, so it's lost. If you wanted to save the data to the host file system, you would have to add the mount option as we add the mount option as we had before. Okay, so now sum.py is part of the container image rather than something that's available at runtime from the host file system. So when you distribute that image and maybe push it up to the Docker Hub and those sort of things, if somebody downloads it, they'll have your copy of the analysis script, our very stupidly simple analysis script in this sense, which just adds numbers together. Okay. Hopefully that makes sense to you. If you've got any questions, please do let me know. There is a subtlety in the importance of the command order in a Dockerfile. When you run Docker build, it executes the build in the order specified in the Dockerfile. We've seen that it did that steps. The order is important for rebuilding, and typically you want to put your run commands before your copy commands because it builds the layers in order. It becomes important when you need to rebuild the container images. If you change the layers later in the Dockerfile and rebuild the container image, Docker doesn't need it. We saw that it was super quick. It used the cached versions of that layer. So if you wanted to change your image to put in multiply.py instead of sum.py, if the copy line came before the run lines, it would need to rebuild the whole image because it'd know that that first line's changed, so then it has to run the other ones beyond that. Whereas because if you put it at the end and just change that one, it would use the cached versions of the things that take more time. Typically, the run lines take longer than things like copy. And so the thing that's going to change most often when you're testing and building your container images should be the latest things in the Dockerfile, essentially, and that would make it much more efficient when you're rebuilding images and using them. We tried this, we ran it interactively. I didn't actually try to run the command, and I should have done that. So let's try it in here, Python 3 within the container /home sum.py 1, 2, 3, 5, 6, and it will add the numbers together using the script that's encapsulated within the container image rather than one mounted from the host file system at runtime. So it's not always a good idea to put your scripts in the container image if they're the things that change as part of the research workflow. But if there's something gone wrong with the formatting here, I'll talk about that in a moment. But if you want to add scripts in, they typically, particularly if they're only small scripts, they don't add much to the size. And if they're a key part of the research workflow, that the script as is important, then you should certainly consider strongly adding it to any container images that you want to distribute. And the warning here, and I don't know why the formatting's gone funny. Apologies for that. I need to we can tidy that up. But you should never put things like login credentials, such as passwords, tokens, secure access tokens, or other secrets inside your container images before you distribute them. Because if secrets are stored in there, most images that get pushed up to Docker are public, and even the ones that are that may be private, that you've got a private repository, if you're paying for access to Docker Hub, can still be exploited potentially and go out as a security problem. So you should never put your security secrets within a container. You could set up your container to be able to pass them in at runtime if you need to. Yes, unless you want to tempt people to make use of them, which people wouldn't want to do, I'm sure. Okay. Another tip, of course, is that there's different ways to get data from outside into the container image itself at build time, and you can use the run command to do that. So say you've got code or scripts in a GitHub repository, you could run git clone as long as you've installed Git. As long as Git is available in the container image, you might have installed it yourself, or it might have been available by default to pull the code in when you build. Or you could use wget as well to download files from the internet straight into the container at build time. So it doesn't always have to be the copy command. You could use the run command with things that actually pull data into the image at runtime to get data in. And as I say, these ones might depend on these commands git and wget that may not be available in the container image you're starting from. So you may need to install these beforehand with like apt-get git or apt-get wget, depending on what distribution of Linux you're using. So there's some other things down here. I'm not going to cover them in any detail in this. You can read through them, and you feel free to ask questions on them after you've had a read through them, either tomorrow or in the course chat or things like that. To make the Dockerfile more useful and fancy, for example, you can create, you can set up the command so it automatically runs the sum.py script, and it tells you how to do that there, and some of the there's some weirdness around entry points and things that you need to do to make things happen, and overriding entry points, adding some .py to the path so you can run it directly and things like that. There's also this link that's very useful for with 10 simple rules for writing Dockerfiles for reproducible data science, which gives some really good examples of best practices used when writing Dockerfiles. And the GitHub repository associated with that paper also has a set of example Dockerfiles demonstrating how the rules can be applied. So that's a good place to start if you've not written Dockerfiles before and you want some ideas of the best way to go about it for reproducible research. What I'm going to do now is stop for a break again, because we've been going just about an hour solid since we came back from lunch. So I'm giving people 15 minutes or so to get a drink, a cup of tea or coffee. I don't think I'm going to get coffee, so I'm still awake by the time we get to the end of this course, and maybe get some sugar or something like that to keep me going too. But we'll come back at 15 minutes past, so just under 15 minutes we've got. As usual, I'll stay here for a minute in case people have questions, and then we'll move on to the final sessions for today for the course, and then everybody's free to escape and think about things other than containers for a while until tomorrow anyway. So I'll see you back here at 15 minutes past. If not, if you've got questions and things like that you want to ask, I'm going to stick around for a minute, and you feel free to ask them. Hi, Lucy. Yeah, you have a question?
Yeah, I do. I'm thinking about people that don't have admin rights on their computer, which it's an issue at the institution I'm at. And I know we're going to see Singularity tomorrow. As another workaround, I guess it would be possible to combine Docker with a binder hub. Have you known people to do this? I don't know if you're familiar with binder.
I have come across binder, but I've not used it myself. I've heard of it. So binder is a way to host Jupyter notebooks. Is that right, or am I misremembering?
I think you can go even further than that. That's how I've used it in the past. Yeah. So I mean, you can specify a GitHub repo, and then it allows somebody to kind of spin up a virtual machine.
Yeah. The other way to do things if you don't have a computer where you have admin access is obviously to get some sort of access to resources in the commercial cloud, where you can definitely have root access because you get a virtual machine then running in AWS or something like that. Now that has its own complications and isn't totally trivial, but they do have generally a free tier where you can use things, or a very cheap tier. You don't generally need a very powerful VM to be able to build your own Docker images. The other option for that is your own institution might run some sort of cloud-like service where you can get access. For example, I know up in here in Edinburgh we have there's a cloud called Eleanor, which researchers can apply for access to, and then you get a VM where you've got root access and you can install Docker, obviously, and build images.
Yeah. Thank you.
I've tried building Docker containers within Singularity containers, and that seems to meet the requirements on our HPC.
Okay, I've not tried that around. I mean, you're going to see tomorrow building Singularity containers within Docker containers. So you'll see the opposite.
A little bit roundabout, but it's actually not too bad, and it gets around some of the security issues that HPC is usually concerned about.
Okay. Yeah. So there are some options. So some of them are non-ideal, and I know that, for example, that you can use some of the I think some actions in things like GitHub, right, to automatically build containers as well. So,
Yeah,
so if you put your Docker hub in a GitHub repository, then you can build an action that will allow you to use the VMs within GitHub to build the container image for you.
Mm-hmm. The use case I'm thinking of is when we publish a paper, just really trying to maximize reproducibility so that when someone reads the paper, they can very easily just run our Jupyter notebook for analysis with everything installed.
So you can push your, I mean, we're going to talk about that right now, actually, where you can put images and how you can enable reproducibility. I mean, for example, you can put them on the Docker hub, but that's not ideal, and for reasons we'll talk about in a moment.
Okay.
Let's carry on with that. Okay, there's some question there from Joris around the last example of the fancy Dockerfile. Do you mind if I carry on with the material for the moment and have a look at? We can have a look at that afterwards. Maybe if we get a chance at the end of the course. Fine. So we've spent a lot of time today talking about the mechanics of using Docker containers, and we have mentioned reproducibility and various aspects of that along the way, but they've been more of an aside. And this course is called Reproducible Computational Environments. So this section towards the end of the course talks a bit more explicitly about what reproducibility means for containers, particularly from a research, scientific research software stance, and from sorry, somebody's banging. My daughter's banging on the window outside, which is distracting me. From a software sustainability, from a software reproducibility stance and a scientific reproducibility stance, and what that actually means. So, one thing I would note here is that this sort of area of reproducibility is still an area of ongoing investigation, and there's no sort of, I think, particularly accepted way to do this. People have different approaches and have put different approaches in for this, and it's still an area of active discussion within the research community. But first of all, I want to define what I mean by reproducibility here. So I think it's hopefully at least reasonably obvious, but what I mean here is the ability of someone else or your future self to be able to reproduce what you did computationally at a particular time, be this research analysis or something else, as closely as possible, even if you don't have access to exactly the same resources in terms of hardware, computers, and things like that you had when you did the original work. And hopefully that makes it pretty obvious why containers are a reasonably attractive technology to help here, because the same computational work could be run across multiple different technologies seamlessly, Windows, Mac, Linux. You can save the exact process that you used for your computational work rather than relying on potentially incomplete notes. You may not have noted how you exactly installed something, what versions was installed. All that is captured in the container image if you save that. You can save the exact versions of the software and the dependencies in the image. And you can access legacy versions of software and their underlying dependencies, which may not be generally available anymore at the time when you want to rerun the analysis. Maybe you want to compare what it would be on a new version of the software compared to what it was on the original version of the software in terms of results. And depending on the size of the data, you may be able to store a copy of key data within the container image itself. This tends to lend itself more to, as I mentioned before, things around configuration options and settings and parameter settings and things like that, rather than large data files per se. But you can at least capture that sort of information, which is when people describe their research in papers, is often that level of detail is missing. Often missing or is incomplete in the paper because you have a certain word limit and you can't include all those sorts of details, whereas you can in the container image. And you can archive and share the container image as well as associating a persistent identifier with it, so other researchers can reproduce and build on your work and cite it properly, and all those sort of things. And actually you can point and say, that is the container image I used, not random one that has a similar name out there on the internet that you might have searched and found. It's this one here that this identifier points to. So we've already seen that the Docker Hub provides a platform for sharing container images publicly, which is great. I mean, it's well integrated with Docker. You can use Docker push and it seamlessly uploads stuff. It's actually quite efficient because it notices when you're using stuff that's already on the platform and doesn't bother to upload that. It just references it instead. That's great. So once you've uploaded this container image, you can point people to its public location. They can download and build upon it. So this is fine for collaborative day-to-day work. Generally a good option for long-term archive of container images from a reproducibility standpoint. Oh, sorry, I lost internet connection a little bit there. From a reproducibility standpoint, for a few reasons. One is that free accounts have a limit on how long a container image will be hosted if it's not updated. So if you leave it for a few months, it will just be deleted, disappeared from your account if you haven't posted an update to it, and those sort of things. It doesn't support an easy way of adding a persistent identifier to container image. So, you know, there's no way to say that this version is the image that I used, and here's the persistent identifier that's going to live for a long time that points to that. And it's very, very easy to overwrite tagged container images with newer versions by mistake. And with the Docker push command, it does not store a history. If you give the same tag to an image and then push it again, it just overwrites it, and the one that was there beforehand is lost. So you can have something that looks like it's got exactly the same name, but is actually a totally different container image from the one that you thought you were using, or that you were pointed to in your research paper or whatever. So when you publish your work and make it publicly available, you can make a container image that you use for the computational work available in a sort of immutable, persistent way, and have an identifier that allows you to point to it. And there are various services for doing this. Your own local institution may have ways of doing this. One sort of cross-institutional or publicly available one is a service called Zenodo that many people have come across. Zenodo is a way of uploading data sets and tagging them. It provides a service for uploading data sets and tagging them with a persistent identifier, so you can refer to them specifically over a long period of time. And one of the formats that Zenodo supports the upload of is a tar archive, which is an old, if you're familiar with Linux, you'll have come across tar. It's an old Unix tape archive format, but it's used quite consistently for sharing data and combining data into a single archive file and then compressing it and then being able to share it. And Zenodo supports the upload of these tar archives, and we can capture our Docker container images as tar archives using the Docker image save command. So using the kind of Docker image save, for example, here, if we took our Python one, we may have latest, we may have a various tag, we don't have a v1 at the moment. You could say, I want to output this to a tar archive called alpinepython.tar. So let me try that. So show you how it works. So Docker container, sorry, Docker image, of course, because we're working with the image, save and alpine Python. The one I have is called latest, I'm pretty sure, and I can minus O to alpine. Okay, and that'll take a wee while to write out. It's just quite, and we'll create a file there with it, and we can see how big it is. So it's 130 megabytes at the moment, so that's quite large. Zenodo does support large uploads up to 50 gigabyte data sets, which isn't massive, but is usually big enough for some images. But you may often need to compress the data to make it fit on Zenodo, so you can use gzip or something similar to do that. So I can gzip and compress the data, and that'll take a moment to run. Okay, and that's reduced it to 50 megabytes, so it's less than half the size that it originally was, which makes it easily fit on Zenodo. And once you've got your archive, you can deposit it on Zenodo. So there's instructions on Zenodo on how to do this. And this does two things. One, it creates a long-term archive snapshot of your Docker container image, which people, including your future self, can download and reuse. And instead of Docker pull, you would copy down the tar archive and do it. There's a corresponding Docker load command to the Docker save, where you can Docker image load, where you can pull in the tar archive of the image into your own local installation. But also it creates a persistent DOI, a digital object identifier, that you can cite in any publications or outputs to enable the reproducibility that points at that specific version, and also allows people to cite it if they build upon your work. So it says, in addition to the archive file of work, that you provide some basic metadata. So there is a way to test the upload. I think it's Sandbox Zenodo. So I can show you how this works without actually creating a real persistent identifier. Again, closer up Zenodo. So I can log in, I think, and you can log in with GitHub or whatever, hopefully. It seems to be going a bit slow. Okay, I'm logged in now, I think. Yeah, so it knows it's me. And then I can upload some data. So I've done various things before. You can see the last time around this course, I did a test container upload. So let's create a new upload. And I can drag and drop files here, or I can choose the files. So let's choose some files, hopefully. And where were they? They were in. It was here. Temp. Containers course. Docker. Docker intro. Some. And there's my targz file. So it tells me how big it is. And then you can add community names if it's linked to a particular community. You can say what it is, whether it's a data set, in this case it's some software probably. Give it a publication date and a title. You specify some authors. Oops, in this case it's me. University of Edinburgh. You can put in your ORCID ID and all those sort of things. You can enter demo, put in some text. And actually various things like versions and languages and all these sorts of bits and pieces, and what access you want and what license you want and all that sort of stuff. And all you can save a minimum amount. So I'm obviously missing some required. What am I missing? Something red I'm missing somewhere. We see how it sort of works. I can try and find out where. So the others are all optional. So it must be that I've just typed something in wrong somewhere that doesn't quite match up to what it wants. I bet I've got the author wrong. Yeah. Will that let me do it now? No, I'm still missing something. Okay, but I've done it before, but it's pretty self-explanatory. Once you're in there, you can add the data you want. You can add in the information associated with it, and what you'll eventually end up with is a digital object identifier. So if I go back, I can show you the one here. So it gave me this identifier, which will always point to exactly this version of the container stored on Zenodo. Okay, to help make things more reproducible, to make things more, to make sure people get the exact version of the container that you used when you did your original work. So, in terms of good practice, the general advice from this area, noting that this is still an evolving area, and more good practice will come out, and guides will come out as time goes on. Making use of container images, computational environment required for your work is definitely a good thing to do if you can manage to do it. We'll talk in a moment about granularity for the container images and the computational work, because this is going to be different from each project or area that you're working in. Have a look at what people do already around containers in your area, and decide on what the right building blocks for the individual container images you're going to use in your work are. Document what you've done and why. These comments can go in the Dockerfile, and the use of the container image, describe the associated documentation and/or publications. Make sure the references are made in both directions. So the container image points at the work that was done with it, and the work that was done points at the container image, and they're all linked together. And when you publish your work in whatever way it happens to be, use an archiving service and a DOI service such as Zenodo, or one at your local institution, or another one that's made use in your research field, to make sure your container image is captured as it was used for the work, and that obtains a persistent DOI to allow it to be cited and referenced properly as well. And then one of the points there I mentioned was the container granularity. What do I mean by that? So one of the decisions you'll need to make when containerizing a research workflow is what level of granularity you wish to employ. So the two extremes of this sort of decision can be characterized in this way. So you can create a single container image that contains all of the tools you require for your research and the analysis workflow. So in terms of what we've been talking about before, if at some point you use Python to do a bit of data cleaning and data manipulation or something like that, and then use R to do some statistical analysis, then your container image would have to contain both Python and R with all the toolkits that they require. Or the other option is to create many container images that each run a single command or step of the workflow, and then use them together. So in that case, you would install your Python data cleaning bit in one container image, your R analysis bit in another container image, and you would specify how you would use them in sequence or in tandem to use the whole workflow. They're the two extremes, right? I mean, you could even, but you could have things that are halfway in between. But in order to decide what the right granularity to use is in your case, like I said above, one of the first things to do is, what do people normally do in your research area? What is the granularity? If people have been using containerized workflows, what is the granularity they're already using? Now, depending on your research area, that might be well developed and understood, or it may be that nobody's been doing this before. So you're sort of on your own with that sort of choice. And in that case, the other point of the decision is what makes sense. Generally, the level of granularity you want is how you clip the different container blocks together in a workflow. They could, if the data cleaning is always the same, but the R analysis bit changes, you might have one data cleaning container image and then multiple analysis container images, depending on what type of analysis you do on the data that comes out the other side, for example, and then they could be swapped out easily within the workflow without having to capture everything in one big after you store everything that you might need for different types of analysis in one container image. Most real applications sit somewhere between these extremes. So there's the positives and negative, the sort of positive and negative points of the different approaches are, for a single large container image, some of the advantages might be it's simpler to document, the full sets of requirements are packaged in one place, so they can't get separated out. It's potentially easier to maintain for one person in particular. That could be the opposite if you're working with a large distributed research group. The disadvantage, one of the big ones, is they could get very large in size, making it more difficult to distribute. As I mentioned earlier, you can use this multi-stage build process, which builds things in your containers and then strips out the bits that you don't need at runtime, that you only needed for building the software in the container, to reduce the size of the image as much as possible. You may end up with the same dependency issues within the container image from different software requirements that you had before. So say you had two different packages you wanted to install, and they had competing underlying dependencies on the same underlying tool or library, and then you're back in dependency hell of the single computer. It's just within the image, within the container itself, instead of in your host computer. So that can be problematic. It's potentially more complex to test, and it's less reusable for different but related work often. It's very specific to the task it was being designed for. In terms of multiple smaller container images, the advantages, I guess, the individual components can be used for different but related work. You can clip them together in different ways and use them in different sequences to enable different types of workflows. The individual parts are smaller in size, makes them easier to distribute. You avoid these dependency issues that you might get within one single large container image between competing pieces of software, and it may be easier to test. You can imagine how you design sort of simple unit tests for each container step. Disadvantages may be more difficult or more complex to document. It's potentially more difficult to maintain, but that might not be true if you're working with a large distributed group. So, for example, different people in different groups, or different people in the same group are responsible for different bits of the analysis of the research workflow, then having separate images actually for those individual steps might make more sense. And you might end up with dependency issues between the component container images if they get out of sync. It can be a bit more overhead to manage and understand what a release of a research workflow means in terms of having multiple container images associated with it. So we're sort of getting towards the end of the lesson, the end of today's session now. There's some steps here at the end the things, which if you to which sort of emphasize thinking about your own research and where you might be able to apply containers and how that might happen and what you could do with them going forward. What I do have at the end is a quick demo of a sort of container real world use case. It's not very researchy. Sorry, there's a couple of examples here that we can talk about. I'm going to look at the Jekyll website one. It's not very researchy, but it does demonstrate the power of containers. But before I do that, what question are the questions people have about the reproducibility and the archiving and that sort of stuff that I've just talked about with, I showed Zenodo, but there are other services out there. Yeah, Brian.
I was just wondering if you could maybe talk for a second about, how Docker and even Singularity can be used in workflow dedicated languages like WDL or Nextflow or SnakeMake, and wondering if there is a sort of Docker branded version of that where it's like a sort of I guess you would call it a multi-stage Dockerfile instead of having a dedicated workflow language. Like, what are the differences there?
So I'm not a big expert in the workflow languages. You mentioned it. In fact, I'm probably the only one I recognised out of them off the top of my head. Ted was SnakeMake, which I've come across before. I think it's hard to comment in general. Yeah, I think it sounds like a bit of a get out for me for this question, but I think it's difficult to comment in general because there's so many things it depends on, right? Fundamentally, one of the key things it depends on is not really a technology choice at all. It's really what is accepted practice in your research area. If that's not saying you never use containers and things like that, but if it's accepted practice that you can document and essentially achieve the same thing in terms of reproducibility around workflows by using a specific tool, and that's what it's used in your research area, it may be that that's a more appropriate way to go. Now, that doesn't mean containers are no use, because those specific tools may be difficult to get working on different platforms, be it local platforms, be it remote HPC platforms. And it may be, that actually the easiest way to get around that problem of getting that bit of software up and running on the platform you want to use it on is to containerize it. And that comes from a slightly different, that's less about the reproducibility side that we talked about, but more about the convenience of, I don't want to have to fight through all these horrible installation steps to get it up and running. I could just go ahead and use a Singularity container on an HPC system rather than have to fight with all the old versions or random versions of compilers they have, and the fact that I don't have root access to install stuff.
And as far as I understand, I played around a little bit with some of the NF Core Nextflow pipelines, and they use Docker containers and Singularity containers in different ways. Some of them have one container that has everything, all the tools you'll need for all the steps. Another strategy is to generate lots of little containers that do different things that can then be sent off to different cores and run on those. And it just occurred to me that one of the main challenges that we come across with running these pipelines, even though they're supposed to be working right out of the box, is that just the Nextflow manager itself is not always compatible with our HPC. And so I wonder if in those cases, is it possible or does it make sense to have containers within a container where you have one master container that's sort of designating all these processes, it has Docker installed, and it can sort of do all these things and create smaller containers within it.
Yeah, I have to say, it's not something I've seen done a huge amount, particularly not something I've seen done particularly on HPC systems. I can't think of a technical reason why it just wouldn't work. I think one of the challenges when you get to that level of stuff is, yeah, I think the solution to more those sorts of things, and certainly the way some HPC systems are going, it becomes more then about container orchestration and making sure, you know, you're launching the containers in the right place, and you know, you're being able to use the resource sufficiently. And the solutions to those sort of things are have often all come out of the cloud area. So things like Kubernetes and Docker Swarm, which are sort of beyond the scope of this course a bit, you know, which allow you to specify how different containers link together and can be started up in an orchestrated way, and how they talk to each other and pass data around between each other, and then how they're shut down, and you know, how you scale them with requirements. You know, so say your workflow thing. So Jeremy's just posted the same thing, you know, and allow you to have that sort of that programmatic definition of how your containers work together, which we haven't talked about at all.
Right,
here.
right.
And HPC systems are becoming more cloud-like as time goes on. You know, I mean, more and more of them are supporting things like, you know, start to launch with Kubernetes, or you know, if those sort of things are. The other thing that often comes up with those sort of things when I'm talking to people about that sort of research workflow is that is it just that actually the commercial cloud might be a better place to try and fit those things rather than on the HPC system, because the individual nodes then are on commercial cloud are, you know, are essentially can be HPC nodes, right? They'll be exactly the same technology, but the way the system's architected in the cloud gives you more flexibility in how it's put together, and saves you having to jump through all these hoops that are on an HPC system.
Yeah, because our issue is currently that you know, our HPC is taking the approach of, well, we don't maintain any of the tools anymore, and like the way it used to be was, or way it is for still a lot of HPCs, is that, you know, they have a team that's dedicated to installing all the latest versions, having different versions available of every tool that people need. And now ours is just kind of taking the approach of like, well, here's Singularity, here's Conda, you can make your own environments and containers, and we don't have to do anything. But now we don't even necessarily have the updated version of Singularity or Java, which is required for us to do this to begin with.
Yeah, yeah. No, I mean, that's really trying. I mean, there does need to be some. I think essentially at some point there needs to be some level of support for what you know. Yeah, it's quite challenging then, right? Because you still need to be able to, as you say, orchestrate things in some way, and you need some sort of higher level software to do that. Be that something more HPC, you know, like the batch system, and how do you integrate running containers and orchestrating containers with the batch system, or be it something more cloudy like Kubernetes and Docker Swarm, Docker Compose, those sort of things. Sit there. So I mean, I think when you get down to that level of stuff, I think it is more a conversation, an in-depth conversation about what makes sense for your research workflow, rather than a generic, this is the right way to do things. Because it depends on which types of resources you have access to, what your workflow actually looks like a bit, and those sort of things. It's hard to be quite generic.
Cool. Well, thank you.
Sorry, I'm not sure that was the most helpful answer. I think if somebody came to me with that sort of problem, I would be saying, can you find funds to run on commercial cloud, or can you look for a more cloud-like facility? I think, because then you can start to use things like Kubernetes and these sort of things that are actually designed to do exactly what you're talking about.
Yeah, we're looking into that, but it's just the HPC is just so much more cost-effective, and maybe not in terms
of
like,
it's already been bought and it's there already, right?
If you have a limited budget, you're kind of stuck with the HPC.
Yeah. I know, for example, some of the HPC facilities in the UK, particularly, for example, we go down to Cambridge, they have, as well as their HPC facility, they have alongside a part of the HPC resources, and they're moving, I think, to making it much more flexible, is available in a sort of cloud-like way, but with the high performance interconnect and all that sort of stuff. So it allows for a different type of workflow to be ported on, than without having to jump through all the hoops that you'd have to get that sort of novel workflow running on a old-fashioned HPC system. Okay. So we've got about 10 minutes left. So the question is, I'm happy to answer more questions on people. So so Lorenzo has more question. Okay, so Lorenzo has asked, I've got a practical question. So when we start a project, should we create a Docker container as the first thing and then develop inside it, including updating the container with more packages as needed? So again, generically, if you're deciding that you're going to containerize the workflow or the research workflow, then I think the short answer to that is sort of yes, right? Is try and start by setting up an image which has the basic tools you need, and then modify it, modify the Dockerfile and iterate towards the container image that works for you and containers using it, because that helps you in the long run, rather than, because if you don't do that and you start on your native system in the traditional way you would, and you start installing software packages and you fiddle about and you're like, that bit didn't work, so I've taken a few steps back and I've gone a few steps forward down another channel, then you run into that problem that you've had before about documenting and missing out documentation steps. So when you come to create your image container at the end, you might have incomplete documentation as to how to get to that from all the sorts of backtracking and fiddling about you've done. I think one approach that people have seen people use before that probably works reasonably well and sounds like a good thing. The Dockerfile is just a text file, right? You've seen that. So that lends itself very well to putting, for example, in a GitHub repo. So what you could do is you could start with a repo with the Dockerfile in, which you're using to build your container, and then as you change the Dockerfile, you're committing to the repo, and you've got a history of what the changes are you made to that Dockerfile in terms of designing the container image. Okay, so as well as the actual, you end up with the right container image, you also have within the GitHub repository the history of all the changes you made to get there. Okay. As Ephemios says, if you've got a defined pipeline, then it's easy to start with the container each bit. But if you're experimenting, you can use, for example, virtual M's, various Dockerfiles, modules, and link together. But most of these things, even VMs and things like that, could be defined by text files. So I'm a big advocate of storing that stuff in GitHub, fundamentally because I'm reasonably lazy. I don't like writing a lot, and if I store them in GitHub or do my commits there, I've always got access to the history of what I did without actually as often having to write things down in a notebook, or forget to write things down in a notebook, and then just you're knackered at the end of the day, you didn't quite write it down, you come back the next morning, you can't remember exactly what you did. And GitHub saves me from my own laziness in that sense. So I am a big advocate of that. So Luke asks an interesting question. So is there a standard container image or Docker image that would be suitable to replicate ARCHER2 Cray Linux environments? So of course, one of the challenges with many HPC systems is they are not standard Linuxes that are available out there. And ARCHER2 is particularly prone to this because it's an HP Cray system, which essentially because HP bought Cray. So it's very, very custom and different. It includes the Cray compilers, it includes lots of tools that aren't generally available. And the way it's all linked together is quite different from standard Linux and even other HPC systems. So the short answer is yes and no. I say that because we've just been participating in an evaluation exercise with HPE to understand what a containerized Cray programming environment would look like and what use cases it would have. And then HPE, based on that feedback, are looking to decide how they're going to productize such a thing and roll it out to people. So the things we've tested are using the Docker image. There's a Docker image and a Dockerfile. Using those as part of, for example, a continuous integration workflow, so people, when they change their code, can have actually the Cray programming environment available within their CI workflow on, say, GitHub or something like that, and automatically test builds. The other use case we've been looking at is, say, a new program environment's released. How will user programs work with that? How will that work for users on the system? Are there any will that cause any problems? Will it, before we install it on the system, we can then give people the container image, and they can test things, or we can test things as a service before we actually go ahead and put all the efforts into installing it on the service properly. It gives us a lightweight way to quickly check if it's worthwhile to install it, or whether that's going to cause big problems for the service. So the answer is, it's in development. I think it's still unclear how it's going to be distributed to users of a system like ARCHER2, but it is something that's under active development by both HPE and the various sites that run Cray EX supercomputers. If you're interested in testing it, we do have some scope to give it to users as long as they use it on ARCHER2. At the moment, they can't take it onto their own host systems, but we can give you access to it to have a play around on ARCHER2 itself. It'd be a Singularity container on ARCHER2, because obviously it's Singularity, not Docker. But if you're interested in it, please just drop a note into the service desk and mark it for my attention, and we can give you access to that to have a play around with if you're interested. Okay, so perfect. So actually, we've come to we're just about the end. There's just a few minutes left before we're supposed to finish today at 4 o'clock. I was going to show containers in action. I could do that very, very quickly if people are interested. But if people have other questions, I want to make this useful to people rather than showing them something that's not particularly useful. So I'm happy to answer questions instead. So maybe actually a better use of the time is to answer any questions people have, and look back over the questions we've had previously in the session, and see if we can answer them rather than do this example, which you could follow through yourself. I mean, the material's up there. If you wanted to have a go, you can. Essentially, it shows you how to use what's called Jekyll, which is the underlying technology used in GitHub pages to build websites. There's a pain. Sorry, I almost said a rude word there. Jekyll is a real pain to install on any system and get up and running, and you end up with lots of dependency issues. But you can essentially circumvent all that just by using the Docker image that the Jekyll people distribute on Docker Hub. So you're able to locally test builds of websites that are on the Docker that go into GitHub before you actually roll them out onto the site. And people can have a look at it if they want. I know there was a question earlier about adding a mount onto into an already running container. And I've not tried. So I think it's very difficult. I did do a bit of searching around on this, and I think it's very challenging, because one of the founding principles of the container is once it's running, it's isolated, and you can't fiddle about with it. That's a security feature. So if it's okay, so what I think you have to mount essentially when you start the container is the short answer. Trying to do anything and extra mounts in a running container is a big security hazard, and so it is not really exposed in a useful way. Okay. So the other thing I should say, because maybe people have to leave it at 4 o'clock and things like that, and I know some people already are, is we're starting again at 10 o'clock tomorrow morning with the Singularity part of the session. Yeah, so as Jeremy says, we start 10 a.m. UK time on the Singularity stuff, which Jeremy's going to lead. If any questions on the Docker stuff occur overnight and you have them, then please feel free to bring them along tomorrow. Type them in the chat. I can answer in the background or in the shared note while Jeremy's taking on the Singularity material. So if you've not had a chance to ask something or something else occurs, please do bring the questions along tomorrow. But otherwise, we'll see you then. As before, I'll stick around for a little while now if people have more questions, but we're at 4 o'clock, so we'll let people leave now.
Hi, I have a question about tomorrow.
Yeah.
I don't install Singularity to my laptop Mac. It is Mac, so will we use Archer tomorrow, or should we try installing locally?
No, so the plan is that we'll get people logged into ARCHER2, so they can use Singularity there. This is supposedly the strength of Singularity. In terms of building Singularity images, what we generally recommend people do is use there are Docker images that have Singularity inside them. So for most people, we'll use your existing Docker installation to build Singularity containers container images that we can take onto ARCHER2 and run there.
Okay, great. Thank you. Bye. See you tomorrow.
Bye-bye.
Thank you, Andrew.
Thank you all for your great questions as well. It's been really interesting group with really interesting questions and things to explore.